up till now we discussed one of the very special cases of electromagnetic waves, that is transmission lines. We introduced the concept of space in the circuit analysis, and we saw naturally the electrical quantities like voltage and current exist in the form of waves on the electrical circuits. However, the concept of voltage and current is applicable to the bound structures like electrical circuits, where you have conductors separated by dielectrics like coaxial cable, parallel wire transmission lines, and so on. If I go to the media which are infinite in extent or semi-infinite in extent, or if I consider a medium which is only dielectric, then the concept of voltage and current is not very attractive. In fact, in many applications it is very difficult to define these quantities like voltage and current. In this situation, essentially we have to go to the more fundamental quantities, and that is electric and magnetic fields. So, having now got some feel for the wave phenomena, albeit for a special case like voltage and current waves, now we will make a departure to the more generalized phenomena of electromagnetic waves, and that is the waves in the form of electric and magnetic fields. So, here onwards now we discuss the phenomena of electromagnetic waves in the form of electric and magnetic fields. You will appreciate that whatever we have done so far, the analysis for voltage and current, that was essentially dealing with the quantities which were scalar quantities. Voltage is a scalar quantity, current is a scalar quantity. If you however go to now the general fields like electric and magnetic fields, these quantities are vector quantities. So, essentially now we have to deal with the analysis of these quantities electric and magnetic field, not on a one dimensional structure like transmission line, but in 3-dimensional space. So, to get the formulation for the vector fields like electric and magnetic fields, let us first revise our concepts of the vector calculus and vector algebra. Before we go into the vector algebra and vector calculus, let us first start how we can represent a 3-dimensional space, because ultimately we have to represent these quantities electric and magnetic fields in the 3-dimensional space. So, there are 3 major coordinate systems which are used for representing these electric and magnetic fields, and these coordinate systems, one of them is what is called the Cartesian coordinate system, which is having 3 orthogonal axes x, y, z. So, if I imagine an unbound space, 3-dimensional space like a box, then the 3 axes will be the 3 edges of the box. So, we have here x axis, y axis and z axis, and the sequence is x to y to z. So, when we write a coordinate of a point in the 3-dimensional space, we write this is x comma y comma z. While defining this axis, we follow certain conventions, and one of the convention we will follow throughout our discussion, and that is this coordinate system is a right-handed coordinate system. What that means is, if we point our fingers of right hand from going from x to y, the thumb should point in the direction of z. If I point my fingers from y to z, then my thumb should point in the direction of x, and if I point my fingers from z to x, my thumb should point in the direction of y. So, this convention later on when we define the vector operators will resolve some of the ambiguities for defining the direction of the vectors. So, in this case we visualize the 3-dimensional space as a box, we follow this right hand convention, and as you can see here, if I take the horizontal plane which is x y, and if I point my finger from x to y, my thumb will point upwards, so the z direction is upwards. Then at each location I can define a vector which is represented by an arrow, and we will come to that what convention we will follow in this course for defining or writing a vector in 3-dimensional space. So, these 3 vectors which we call as the component of a vector at that location, that will be pointing in the 3 coordinate axis. So, you will have for any vector a component along the direction of x, which will be x component, a component of the vector along direction of y, which will be y component, and a component along z will be called z component. So, any vector now can be resolved into 3 components. So, a vector essentially can be represented by a set of 3 elements. First element of that set will denote the component of the vector in the x direction. The second element will represent the component in y direction, and the third component will represent component in z direction. So, whenever we write a vector now in 3-dimensional space, just for visualizing a vector or electric or magnetic field, which are vector quantities, in fact you require a whole lot of imagination. You can write down the mathematical expressions, but ultimately it will be a good idea to visualize this vector in 3-dimensional space. And if we do that, and if we develop a practice of visualizing these fields or vectors in 3-dimensional space, then the subject of electromagnetic waves will be more fun than a burden of mathematics. So, the idea here is to visualize these vectors or whatever phenomena we analyze immediately in 3-dimensional space, and when we do that, then there will be much more physical insight in the problem of electromagnetics than simply getting lost into the mathematics. So, idea here is to get a physical feel for the vectors, and then whenever we solve a problem, we make sure that we do not lose touch with the physical aspects, though we will be doing rigorous mathematics, which will be the vector calculus and vector algebra. So, the simplest coordinate system which we see here is a Cartesian coordinate system, and the important feature of this coordinate system is no matter where you go in the space, the direction of these vectors along x, y and z direction, they remain same. So, if I take a point from here to here, the x vector will still point this way, y will point this way, and z will point this way. That may not be true for when we go to the other coordinate systems. So, we will write down essentially the vector relations for the Cartesian coordinate system, because that is the coordinate system which is rather easier to visualize, and then as and when we require other coordinate system, we will use the vector identities in that coordinate system. The second way of defining the coordinate system is what is called the cylindrical coordinate system. That is, if you imagine the 3-dimensional space like a big cylinder, then this is the axis of the cylinder and the space is imagined like a cylinder. So, if I write the same Cartesian coordinate system x, y, z, the plane passing through x, y will be perpendicular to the axis of the cylinder. So, this plane x, y will be perpendicular to the axis of the cylinder. Then a point P, the coordinate of a point, we can find out as the radius vector. If I drop a perpendicular from this P on this xy plane and measure the radial distance of this projection of the point on the xy plane, that distance we call as r. The angle which this radius vector makes with the x axis, as we call angle phi, and from this point, which is a reference point as the origin, the distance which we travel along the axis of the cylinder we call as the z point. So, we have got a coordinate system in this case with a sequence which is r, phi and z. Again we follow the right handed coordinate system. So, if I write a vector, then from r to phi, if I point my fingers from r to phi, I must get z direction. If I point my fingers from phi to z, I must get r direction, and so on. However, how do I define this direction, the phi? The direction r and z, it looks quite straightforward from here, that if I take a arrow which is pointing in the direction of z, that is the z vector. Similarly, if I take a vector which is pointing in the direction of the radius vector r, that is the r vector. Phi vector is a vector which is tangential to the surface of the cylinder which is passing through this point P. So, if I take this cylinder and if I draw a tangent at this point P to this cylinder, this direction or this vector is the vector phi. So, at this location I have one vector r which is coming radially outwards from here. The tangential vector to this cylindrical surface will be phi, and the vector which is along the axis of the cylinder will be z. And from here we can see the relationship between the Cartesian coordinate system and the cylindrical coordinate system. So, whenever we have rectangular geometries, we use the coordinate system which is the Cartesian coordinate system. However, if we have a geometry which is cylindrical in nature, like a coaxial cable, optical fibers, circular waveguides, or many other structure where the geometry looks more like a cylinder, that time the coordinate system will be the cylindrical coordinate system. Of course, we can always analyze a problem in any coordinate system which you like, but there will be ease in analyzing the problem in cylindrical coordinate system if the structure looked like a cylinder. So, generally when we do the analysis, we first choose appropriate coordinate system and then we solve the problem of electromagnetics in that coordinate system. The one thing you should note compared to the Cartesian coordinate system in this coordinate system is, in Cartesian system, as we saw, the direction of x, y, z component of the vector, they remain same everywhere in space. So, no matter where the point moves, the x always orients in the same direction physically. However, if I go in cylindrical coordinate system, the z vector is always in the same direction no matter where I go, but the r vector and phi vector, they will keep changing direction as I go to different locations. So, if I go to, let us say, a point on this cylinder somewhere here right in front, then the radius r vector will be coming towards u, the phi vector will be perpendicular to u. If I go to this point on this cylinder, the rightmost point, then the r vector will be perpendicular to u and the phi vector will be going inside the plane of the paper. So, as we see that in this coordinate system, the vector components r, phi, they change their orientation physically at different locations in space, but the vector direction z remains constant at every point in space. The third coordinate system, which is what is called the spherical coordinate system. In this situation, if you imagine the three-dimensional space like a big sphere, so you have some center of the sphere, what we call as origin, and if you would consider a sphere, here I have shown only one octant of a sphere. So, if I take a sphere and mark a point P on the surface of a sphere, then this location of this point can be now written in three quantities: the radial distance from the center of the sphere, that is origin, and the vector which are tangential to this surface in two perpendicular planes. So, let us say if this point was P, I drop a perpendicular from this P on the xy plane, the radius vector which we have here from the origin to this point where the perpendicular is dropped, if I measure the angle from the x axis of that vector, that angle we denote as phi. So, we have this vector here which is the distance r from the origin. So, this is the first coordinate. The second coordinate is if I draw a tangent to this surface of the sphere in a plane which is passing through the topmost point of the sphere here where the z axis meets the origin and point P. You will see a cut in the sphere, and that cut will be this cut. If I draw a vector in that plane tangential to the surface at point P, that defines the direction of vector theta, and angle theta is the angle which this radius vector makes with the z axis. So, in the coordinate system we have r, theta, phi, that is the sequence. So, r is the radius vector, radial distance from the origin. Theta is the angle which is measured from the z axis from the radius vector, and phi is the angle which is measured from the x axis of the radius vector, which is found by the projection of this point P on the xy plane. So, in this case now the point is defined by the radial distance and two angles. Compare this with the Cartesian and the cylindrical coordinate system. In Cartesian coordinate system, the location was defined by three distances. When we go to cylindrical system, it was defined by two distances and one angle. If I go to the spherical coordinate system, then the location of the point is defined by one distance and two angles. Again, in this case, the direction we define that sequence that r, if I make my fingers point from r to theta, my thumb must point in the direction of phi. If my fingers point from theta to phi, my thumb must point in the direction of r, and so on. So, see here, if I consider this point P, the r will be radially outwards vector on the sphere. So, if I draw a normal to the surface of the sphere, that will denote the direction r. If I draw a tangent, as we saw here in this plane, so if I take this radius vector at an angle theta, and if I draw a vector perpendicular to this vector going away from this theta, that will be the positive direction of vector theta. And if I take a tangent to this surface in a plane parallel to the xy plane in the direction of phi, that vector will be called the phi vector. So, as you can see here, this angle is theta, this angle is phi. So, if I put my fingers like this, my thumb will be pointing in the direction of r. If I go from r to theta, which is like this, then my finger will be going inwards, that is in the direction of phi. So, we have marked here three vectors r, theta and phi for a given coordinate P. They are marked in such a way that they follow the right hand rule. So, whenever we draw a coordinate system, whether it is Cartesian or cylindrical or spherical, first we must develop a habit of writing the right handed coordinate system, because when we do the vector analysis we will follow certain conventions, and those conventions are all with the understanding that we are following the right handed coordinate system. If we change our coordinate system, all those conventions will go wrong and the directions of the vector will go wrong. So, that is the reason whenever we draw, let us say, coordinate axis, if we say this direction is x and this direction is y, then the direction of z should be, let us say, the xy lies in the plane of the paper. If I point my fingers from x to y, I must get the direction of z which is in the direction of my thumb. So, if I put my finger going from x to y like this, then the thumb points downwards, that means the z axis must go inwards, that is the correct coordinate axis. So, in this case, if I take z axis which is like this is correct, On the contrary, if I had drawn the axis which was like this is x, this is y, and this is z, this will be a wrong convention, because this axis now is not going to follow the right hand rule. So, whenever we draw the coordinate axis, we must make sure that we draw the axis like this and not like that, because this axis does not follow the right hand convention as we defined. The third coordinate system which we have seen here, the spherical coordinate system, it has another special property, and that is, if you take a Cartesian coordinate system, you can shift the origin anywhere in the space, whereas when you define the spherical coordinate system, this point origin is defined, all things are measured from there. If you use the cylindrical coordinate system, then the line is defined. So, basically all distances are measured from that line. So, whenever we have a problem like antennas kind of problem, where you have a source of energy which is sending away the electromagnetic waves and so on, and this source is more like a localized point or a region in the space, this coordinate system is more appropriate. As I mentioned, if I take a structure which is like a coaxial cable or a waveguide or transmission line, where energy is going to flow along the length of the structure, there the cylindrical coordinate is more appropriate, and in some general cases the Cartesian coordinate will be more appropriate. If I consider a closed structure like a closed box, which we will see like a resonator or a cavity or something like this, the Cartesian coordinate will be more appropriate. So, with this understanding of coordinate systems, now we go to the basic definitions of vectors and their operators. Firstly, when we have a vector, as we said, it is a set of three quantities which we call as components. So, any vector can be represented by some three components, some A, B and C, and depending upon which coordinate system I am using, Cartesian or cylindrical or spherical, they will have different meaning, or they will represent the components in different directions. Mathematically, this description of vector is enough, that the vector is a set of three elements. However, when we go to the solution of the physical problem like electromagnetic waves, we would like to visualize this vector in three-dimensional space. Now, vector, this set of three elements, is an abstract thing. So, if I say there is an electric field, it is a very abstract concept. We do not know how to visualize electric field. Same is true for the magnetic field also. So, what we have to do now, we have to give some physical picture for this vector, this abstract thing. So, let us say if I have a vector which is represented by three elements, and we say these are the three components of the vector. The most commonly used convention for this is represent a vector like an arrow. So, if I take an arrow which is having a head and a tail, then I say a vector essentially is this arrow. So, the arrow direction tells me the direction of the vector, and the length of the arrow tells me the magnitude of the vector. So, this is one of the conventions, that if I look at the vector like an arrow in three-dimensional space, then it will have a length, and the length will correspond to the magnitude of that vector, and the arrow will indicate in which direction the vector is pointing. This is if I look at this arrow sidewise. Suppose the arrow is going away from you or coming towards you, then you are looking at this arrow end on, and then the same arrow, if I see from this side, will look like the arrow is like that, standard arrow. So, if I see the arrow from the back side, it will look like that. If the arrow is coming towards you, I will see the tip of the arrow. So, the arrow will appear something like this. So, if I look at the vector and if I visualize that as an arrow, then a arrow going away from you can be denoted by this, and the arrow coming towards you can be denoted by this. So, this is going away, this is coming towards you. So, a vector, its orientation, if it is seeing side on, then it can be either a circle with a dot, that means the arrow comes towards you, circle with a cross, that shows the arrow which is going away from you. As we now wrote the magnitude of the vector, when we are seeing the arrow side on, the length of this vector essentially indicated the magnitude of the vector. If I am looking at the arrow or the vector side on, then how do I look at the arrow? I see only now a point or a circle. So, how do I see the magnitude of this circle? So, many times the convention is followed that the size of this circle will denote the magnitude of that particular vector. So, smaller the size of the circle, weaker or the less is the magnitude. If I make the circle size larger, that represents the larger magnitude of the vector. This convention we will uniformly follow, and later on when we go for visualizing the 3-dimensional fields, essentially we will see the electric and magnetic field as a distribution of these vectors or these arrows in the 3-dimensional space. So, these abstract quantities like electric and magnetic fields will have some physical means of visualizing, and that is what essentially is this framework, that we use this framework to visualize the abstract quantities in the 3-dimensional space. Having understood this now, then we can go to the basic operation of the vectors, and let us say now I define the vector, as we said these are 3 elements. So, let us say, let me describe all the vector operations in the Cartesian coordinate system. So, a vector can be now represented by the 3 components in the 3 directions, the x direction, the y direction and the z direction. So, let us say a vector A, which is denoted by A bar, that is the x component, x cap, I will explain what it is. This is y component, y cap plus z component, z cap. The quantities which are denoted by caps, the x cap, y cap and z cap, they are the unit vectors in the 3 coordinate axes x, y and z. So, if I imagine vector like arrow, and if I orient that arrow in the direction of the x axis, if the length of this arrow is unity, then that vector will be denoted by this quantity x cap. Similarly, if I consider a vector of unit length which is oriented in the y direction, that vector is denoted by this quantity y cap, and same if I take a vector of unit amplitude which is oriented in the z direction, that quantity is represented by z cap. So, these quantities are called the unit vectors. In the 3 directions, the x, y and z direction, and Ax, Ay and Az are the components of the vector A in the 3 directions x, y, z. So, a general vector A in the 3-dimensional Cartesian coordinate system can be represented by the x component multiplied by the unit vector in x direction plus the y component of the vector multiplied by the unit vector in y direction plus the z component multiplied by the unit vector in the z direction. Now, we can define certain operations on the vectors, and let us say I have another vector B which is having component Bx in x direction plus By in y direction plus Bz in z direction. The addition subtraction of these vectors is, if I write A plus B, it is adding the components of these vectors. If I subtract B from A, it will be subtraction component wise of the two vectors. So, the addition subtraction operation is, this will be Ax plus Bx x plus Ay plus By into y, Az plus Bz into z. And the same is true for the subtraction. So, instead of adding these two vectors, if I subtract, then you will subtract B from component from corresponding A components. So, the addition and subtraction of the two vectors is component wise addition or subtraction of the two vectors. The other important operation which we have between these two vectors is the multiplication or the product operations. And there are two product operations which are defined for the vector quantities. One is called the scalar product and other one is called the vector product. So, the product which we define is the scalar product. It is also called as dot product. Which is denoted by A dot B, and that is defined as the component wise multiplication of these two vectors. So, this product is defined as Ax multiplied by Bx, Ay multiplied by By, Az multiplied by Bz, sum of that. So, this will be Ax Bx plus Ay By plus Az Bz. So, the dot product of the two vectors is a quantity which is a scalar quantity. It is sum of the product of the components of the two vectors. That is the reason this product we call as the scalar product of the two vectors. The another product which we define for the two vectors is what is called the vector product. It is also called the cross product. And that is defined as A cross B is equal to determinant of is unit vector x, y, z, ax, ay, az, bx, by, bz. You can solve this determinant and you can get the x component which will be ay bx minus az by. The y component will be bx az minus ax bz, and the z component will be ax by minus bx ay. So, if we expand this determinant, I will get a vector which will be the cross product of these two vectors. And since this quantity is the vector quantity, we call that product as the vector product, and it is denoted by this cross operator. So, this is referred many times as the cross product of the two vectors. We can see immediately that in this case, if I change the order of these, so if I make B dot A, this product remains same, this product remains same, this product remains same. So, the scalar product does not change if I interchange the order of the product. So, from here I see that A dot B is also equal to B dot A. However, that is not true for the vector product. So, if I take this quantity A cross B, that represents a vector, but if I change the order, the magnitude of the vector remains same, but the direction of the vector reverses, which we can see if I interchange B to A. So, A comes here and B comes here. We can work out and see that now the quantities which we have for each of the components, that quantity has become negative of the previous quantity. So, for every component the sign has been inverted if I interchange these two rows. So, if I change the order of A to B, I will get minus B cross A. Now, here again this quantity, the vector quantity, represents a vector which is perpendicular to the plane containing these two vectors A and B. So, if I imagine these two vectors A and B like the two arrows, and if I consider a plane which is passing through these two arrows, then the cross product vector will be a vector perpendicular to these two arrows, or it will lie perpendicular to the plane passing through these two arrows A and B. Question now again is that how do I know what is the direction of this arrow which is the cross product? So, again it is the go by the same convention that if I go my fingers from A to B, the direction of the thumb will represent the direction of this vector cross product. If I interchange the sign B to A, now my fingers will go from B to A, so direction of the thumb will be opposite. So, by interchanging A and B, essentially following the same convention, my direction of the thumb will become opposite, and thus why the direction of the vector will become opposite. So, the magnitude of the vector will remain same, but the orientation of vector will be in the opposite direction. So, these are the two important operations on vectors which we will encounter when we go to the analysis of the electromagnetic waves. Then we require the operators on the vector which are the differential operators. So, consider now a field which is a vector field. That means that every location in the space you define this quantity which is a vector quantity. So, I consider the space and go to any point, and if I measure this quantity will have a magnitude at that location, and this quantity will have an orientation if I imagine this vector like an arrow. Just to give an example of these vector fields, let us say I have a quantity like velocity distribution. Let us say I have air velocity in the medium. So, if I go around me, and at every location if I measure the velocity of the wind, and if I find out in which direction the wind is flowing, I know the direction of that wind. So, I know the strength of the wind movement. I also know the direction in which the wind is moving. So, these two quantities together I can put in the form of an arrow. The strength of the wind movement I can denote by the length of this vector. The direction in which the wind was flowing I can mark by the arrow. So, at every location I have this quantity which is the velocity of air around me, which can be denoted by this vector. Similarly, if I have, let us say, a flow of some liquid, if I go to a various locations, I will again have the quantity which is of liquid which is flowing at that point. Also, we will know the direction in which the liquid is flowing. So, we again can represent that quantity by an arrow at that location. So, if we have a quantity which can be represented by its strength or magnitude, and also it has a direction, then you can call this quantity as a vector field. So, electric field or magnetic field is a vector field. So, if I go in 3-dimensional space and if I measure the electric and magnetic fields, they will have different value in magnitude, and also they will have different orientations. So, if I now consider a vector field in 3-dimensional space, then one can define certain operators for these vector fields. Before getting into the vector fields, let us say suppose I had a scalar field. Suppose I have temperature variation around me, this quantity is now a scalar quantity. But if I measure the variation of temperature, the variation of temperature in different direction is different. Suppose I take a temperature variation right above the surface of the earth, as we go to the higher and higher altitudes, the temperature drops. If I move in the horizontal direction, maybe the temperature variation is not very much. If I travel a distance of our 100 kilometers on the surface of the earth, the temperature will not vary significantly. But if I travel 100 kilometers above the surface of the earth, the temperature variation will be significant. It would drop at least by about 40-50 degrees. So, that means though the quantity temperature is a scalar quantity, its variation is a vector quantity. Its variation depends upon the direction. It does not have any variation in horizontal direction, but it has a variation in the vertical direction. So, if I have now a quantity, scalar quantity, which is a function of 3 dimensions, basically this function is a scalar function of 3 dimensional. But if I find the variation of this quantity, this variation is a vector quantity. So, we can define an operator, the differential operator, what is called the gradient operator, which operates on the scalar field, and the outcome of this is a vector quantity. So, this operator is what is called the gradient operator, and that gives you gradient of a scalar field So, I have a certain function f which is a scalar function of x, y, z, this quantity is scalar. The gradient defines the maximum rate of change of this function in 3-dimensional space. So, if I find out the rate of change of the function in 3 directions, 3 coordinate directions x, y, z, then I can find out the direction in which the function is changing maximally. That vector of the rate of change of this function is what is called the gradient vector. So, this is denoted by a differentiation of the scalar function f, and this differentiation is in 3 dimensions. So, therefore, to represent this operation, we define an operator what is called a del operator. So, we define an operator called as del and denoted like this, that is the derivative in the direction x multiplied by unit vector x plus derivative in the direction y multiplied by unit vector y plus derivative in the direction z multiplied by unit vector z. So, this operator del essentially is a differential operator which can operate on the scalar field, and later we will see it can operate on the vector field also. But if it operates on the scalar field, then that operation is called the gradient operation. So, here the gradient of a scalar function del of f. So, if I take this function f and I take 3 derivatives, this is df by dx, the x direction, plus df by dy direction plus df dz z direction. So, if I take this scalar function and take its derivative with respect to x, this quantity tells me now rate of change of this function, spatial rate of change of this function in the x direction. Similarly, this quantity df by dy tells me the rate of change of this function in the y direction, and this quantity represents rate of change of this function in the z direction. So, this quantity, what is called the gradient of this scalar function f, is a vector quantity, and these are the components of this vector which represents the rate of change of this function along the 3 coordinate axes x, y and z. So, when we have a scalar function and if you want to find out the rate of change of this function, which is a vector quantity, that we can find out from by operating del on that scalar function. The expression which you have written here is for in the Cartesian coordinate system, but similar expression can be obtained for the cylindrical coordinate system and the spherical coordinate system. Let us now say that I have a vector field, and as we mentioned earlier, the quantities like velocity or the flow of liquid or electric field or magnetic field, these are the vector quantities. So, if I have any of these quantities, then I have a vector field. So, let us say I have now a vector field. So, there is a quantity vector f which is a function of x, y, z, but it has components also in the direction x, y, z. So, function x, y, z, it has a component f x, x plus f y, y plus f z, z. So, f x is the x component of this vector, f y is the y component of this vector, and f z is the z component of this vector, and each of these component is a scalar function of x, y and z. So, all these quantities are scalar functions of x, y, z. Then we can define now the differential operator for this vector field, and there are 2 operators which you can define. One is what is called the divergence operator, which is like a dot product of the del operator and the vector f. So, it is del dot f, and that is, as we saw in case of the dot product, it is the component wise product and the sum of all these products. So, this is d f x by dx plus d f y by dy plus d f z by dz. We will see the physical meaning of this little later, but this is like defining the scalar product of the del and this vector field f. As we have defined the cross product, we can define the cross product again between the del and this vector f, and that product is what is called the curl. So, you have curl of vector f, and that is the cross product of the del and f. So, it is del cross f, which will be x, y, z, and if you see here the way we wrote the cross product, it was the component of this first vector and the component of the second vector. we have got for the del, if we treat it like a vector, its components are d by dx, d by dy, d by dz. So we can write here d by dx, d by dy, d by dz, fx, fy, fz. So if we have a vector field, then we can define these two operators called the divergence operator, which is the dot product of the del operator and the vector f. If we take a cross product, then that product is what is called the curl of the vector f, and which is the del operator, a cross product with f, which is given by the determinant, which is like this. So the components can be written, the x component will be dfz by dy minus dfy by dz, and so on. So you can expand this and we can write the component of this curl vector. So curl of a vector is a vector quantity, whereas the divergence of a vector is a scalar quantity. Next time when we meet, we will see the physical interpretation of these quantities, the divergence and curl. And once we get that physical feel for these quantities of divergence and curl, when we write the laws of electromagnetics, that time it will become obvious that yes, if you want to capture those physical effects, then the appropriate concepts will be the divergences and curls. So the formulation of electromagnetic problems can naturally follow in the direction of divergence and curl. So this gives you the basic framework now to define the vectors and define certain basic operations on the vectors in 3-dimensional space.